for inviting me. It's definitely a great honor. There is some return of voice. Okay, now it's not the case anymore. So good afternoon, everyone. It's a pleasure to be here to talk to such a crowded crowd. The plan for today is indeed the one of using tools developed in statistical physics, and especially for the study of glass physics. But the final aim of the application of these tools will be specifically the one of decipher some of the aspects of efficiency or inefficiency in signal reconstruction as it is as it is a problem in the inference problems and in machine learning. And also we will see how these specific tools and know-how that has been developed in glass physics might also be used to understand how to improve some of the algorithms that are used in these fields to make them competitive with what are thought to be the most optimized algorithms. I will refer to the paper that are listed here all along the presentation in correspondence of the different topics. So as I said, the starting point is the physics of glasses. And of course, there is not at all the time for giving a whole review of that, but I want what are the main aspects that we will be using for understanding the follow-up, the problems that we are going to face later on in the presentation. So what is the main aspect? Well, glasses, of course, everyone probably knows in this audience, presents these mechanical properties of a solid while having an amorphous macroscopic structure, which is most typical of a liquid. And well, indeed, the reason for it behaving as a solid is that its dynamics is very slow at room temperature. And in fact, it is so slow that the equilibrium is never reached in the observation timescale. So all we can see is the out of equilibrium dynamics. And there is no time translation invariance regime that can be, again, visible as a realization of the equilibrium dynamics. This is visible, of course, in experiments and in numerical simulation that are realized with simplified microscopic representation of the glasses, and also realized and observed by implementing what it is a Langevin dynamics that starts from the Hamiltonian, uses the gradient of the Hamiltonian to update the position of the particle at each single step, by also adding a noise that would include in this Langevin dynamics the effect of the temperature. So, and the experiment that one can look at, again, in real life and in silico, might be the one of, is the one that is, goes under the name of a quench. What is a quench? We start from an initial configuration, which is typically random, characterized by high energy. And then the temperature that represented by this noise term is rapidly decreased so that the final configuration would be another one, typically a much lower energy, and it is observed the out of equilibrium dynamics, this relaxation dynamics that connects the two. Now, this is again out of equilibrium, time translation invariance is far from being achieved. So one-time quantities such as the energy show a very slow decay, and here you see a logarithmic decay. And other quantities that will turn out to be very interesting for us in the following are two-time quantities like, for example, the mean square displacement. And these develop typically in this kind of slow dynamics. They show the formation of a plateau. And these are, again, two-time quantities represented as a function, this t weighting, which is the distance in time from the initial quench. And this function is represented as the distance between the final time of observation and this t weighting. Now, both these observations are characteristics of a dynamics that gets lower and lower when this distance from the initial quench gets larger. For example, in the mean square displacement, we can see that particles will cover the same distance on a much longer time here, when T weighting is getting larger. So this is a characteristic of this slow dynamics, which goes, of course, under the name of aging dynamics. Interestingly, the same phenomenology can be observed in a mean field model of glassy systems, and this one example for all is this, the one given by the spin-spin model, which is characterized, interestingly, by a very different microscopic description in terms of spins. So the energy is the product of p-uplets of spins coupled with these random elements with zero mean and certain variance. And although the microscopic definition of the system is so different, one can see qualitatively the same feature at the level of the dynamics when observing similar protocol, dynamical protocol, which is the quench. In particular, a very slow relaxation of the energy and the development of a plateau in the two time quantity represented by the mean square variation of this spin variable. Now, interestingly, of course, in this case, we are talking about the actual solution of the dynamics, which is hard, but still possible for this simplified model. And, well, the model is simple enough so that it allows us to have a perspective also on another ingredient here in the game, which is the energy function, represented as a function in the very large dimensional space. So as a function of degrees of freedom of the system, we are going to call this energy profile, the energy landscape of the problem. And it is possible to characterize for such a model the statistical feature of this energy landscape by enumerating the stationary point of this very rough surface. And also, so those are the points where the gradient of the function will vanish, and also distinguish between these stationary points, what are the minima and what are the saddles, for example. This will be achieved by looking at the Hessian, so the matrix of the second derivative, and checking whether the sign of the eigenvalues are all positive or instead are of mixed sign that will distinguish a minimum from a saddle. So I said, in this case, it is possible to perform this analysis, and the result is the following. We have that at the beginning of a quench dynamics, the structure, so the distribution of such eigenvalues that can be obtained in correspondence of the stationary point that are typically visited by the dynamics, are described by a semicircle law, that's such a distribution, which is centered in the origin at the beginning of the dynamics, typically describing saddles with the same number of directions, which are positive and negative, so stable and are stable. But then along the dynamics, this semicircle, which tells that the dynamics is visiting saddles with a smaller and smaller number of unstable direction. This can be represented by a cartoon of this aging dynamics that puts together this aspect of the landscape and the macroscopic observable we have described so far, in which we can describe this dynamics as falling from a very high values of the energy by visiting, so this is the decay in the energy, by visiting saddles with a smaller and smaller number of direction until this dynamics lands on this first layer of minima, which are the most numerous, the highest in the energy level, and also the flattest of all minima, because these correspond to the minima, those minima that are barely stable, or also called marginally stable minima. It's interesting to know that there is a whole structure of other minima that are instead properly stable, but this dynamics will not be able to reach them and to visit them because it cannot go to this further level because it's stopped by the first layer of minima. So this structure, very specific connection between the dynamics and the landscape structure is the central concept of this talk, and we're going to see how we can exploit this connection that emerges in the aging dynamics as described in the P-spin model to understand what will be the performances of gradient descent based algorithms that are also widely used in machine learning and often can be used in inference problems. Although in the second case, for inference problems, usually gradient descent-based methods or algorithms are thought to be suboptimal with respect to others. And here, this will be another of the topics we're going to focus, how to try to make gradient descent dynamics competitive with respect to other algorithms. So this is the plan. And the first playground in which we're going to apply this concept is the one of machine learning, in which we will try to answer at least partially one of the big questions that is around in the field, and which is connected with this question on why machine learning does achieve such spectacular result in the latest implementation. We need a small introduction on machine learning, and more specifically on the task of supervised learning, which is the one we will focus on. And this task is the one of finding a function that will be able to classify images according to specific given labels. For example, the function we're looking for must be such that it will be able to split a vector that has a non-zero component in correspondence of the label of the cat when an image of the cat is given as an input as a collection of pixels in the input of the function. And similarly, the function should be able to recognize a dog when it is given as an input in the form of the image. Now, this, of course, is a very complicated task because of the large variability of figures. But in reality, in practice, the wanted function is searched among a very specific subset of functions, which are the function parameterized according to a specific network structure. Now, in this network structure, the variable in the internal nodes are evaluated as a nonlinear function of a linear combination of the variables at the previous layer with some weights that are parameters of the problem. So this is a way to evaluate all the values of the internal nodes until the final answer of the network is obtained as a result. Now, for a given structure and a specific choice of the nonlinearity, then this means that this whole function is parameterized only in terms of the weights which are sitting on the links. So the one remark here is that we should note that the current realization of such a neural network, this number of parameters is actually very, very large, and we are going to come back on this point. But conceptually, we are ending this slide with this idea that the task of finding this optimal function has become the task of finding the optimal choice of such weights so that the function will be finally able to classify the images. Now, how this optimization is realized in practice? Well, this is guided. So there is a training of the network based on what is called the training set, which is a collection of images that already contain correctly classified. So at the beginning, the machine evaluates its own answer that corresponds to a random guess of the weights. And this answer is compared to the the correct label. And for each image is evaluated an error between the two answers. And it is defined what is called a loss function, which is the sum of the errors for all the single images. For example, the mean squared loss will contain the sum of the mean square errors in this way. So the task of finding what is the best collection of weights now becomes finding the function that will be the correct answer on the entire training set will be the one that is characterized by it corresponds to the weights that will minimize this loss function. Okay, so it becomes the problem of the minimization of a function which is parameterized in this way. Now, a natural way, of course, to do so is the one of using a gradient descent algorithm in the space of all the possible weights. Now, unfortunately, it is not possible to realize that immediately, because what is actually realized in practice is to use this stochastic gradient descent, because the training set is very big. So it is computationally too demanding to evaluate the gradient over all the images. So the gradient is evaluated, is estimated starting from a subset of the image. But we could think of this stochastic gradient descent as a gradient descent with a little amount of noise added. Okay, so it can be thought in this way. So, but once we have said that, maybe you start to see straight away what is, of course, the link with the glass problem that we have started to discuss earlier on. Because again, we are talking about the minimization of a function that depends on a large number of parameters. In both cases, and this will be realized through a gradient descent based algorithm with a certain amount of noise. And also we are looking at this the behavior of this minimization starting from a random initial configuration, as it was the case of quenches. So we have seen how in glasses and spin glasses, the landscape with the many minima that would characterize them determines the specific feature of the dynamics. So the question is, what happens by looking at the learning dynamics? Can we indirectly learn ourselves something about the landscape of machine learning, and whether characterization of this landscape will be able to let us understand what are the good ingredients that has been added empirically to make successful this training procedure as it is nowadays. So this was the plan we had in mind, and we started to look at the training dynamics as it were some glass dynamics in a number of different structure of neural network that were facing the problem of classifying different collection of images. And I show only one example of the result because the other were all qualitatively similar. What we found was we could observe the behavior, the very slow decay of the loss function all along the training dynamics. So this is the equivalent of the energy, which again shows a logarithmic decay. However, in this case, it also reaches its lowest possible value, meaning that it does not get stuck at higher values as we saw it was the case for aging dynamics. And then we also focused on the mean square displacement, which also shows two different regimes. We have at first the formation of a plateau as it was observed in the aging dynamics. However, again, in this case, this aging is interrupted in favor of what it is an unexpected second regime, where this time translation invariance is restored. We don't see the dependence on the waiting time, so the time from the beginning of the dynamics, and also the mean square displacement that becomes compatible with the simple diffusion process. So in conclusion, we can say all this observation shows us that, in fact, training dynamics is exploring a rough landscape, at least at the beginning and for a while. But then at a certain point, it reaches the bottom of this landscape, which appears to have the form of a wide, flat area, where actually diffusion and free diffusion is still possible. And this implies the success of training dynamics, because the deepest possible level of the loss means that all the images have been correctly classified. However, of course, we should remember that this is not what it was not always the case that this successful result was obtained, because already 10 years ago, machine learning was stuck on non-optimal outcomes when it was started to be applied. So the natural question is what happened in the meanwhile. And it's true that one of the big ingredients that were introduced is this very large number of parameters or weights for the neural network. So a natural question is how these dynamics would change by looking at a network that is much smaller than the one that are used nowadays, how this aging dynamics would change. And the answer came from such an observation we made. We observed the decay of the loss function for a smaller neural network, and then the decay was again slower than exponential, so slow dynamics appeared. But then in this case, it was not possible to reach the bottom of the landscape, nor the mean square displacement showed any sign of retrieval of the, reaching of the equilibrium or retrieval of a time translation invariance regime. So in this case, aging remains uninterrupted, which means that in the second case, for this small number of parameters, actually the landscape is actually full of a thick structure of layer and minima. They are back and they are all over the region that is typically visited by the dynamics. And this partially clarifies why the performances of machine learning have so much improved by introducing more number of parameters, because they were, so this added number of parameters, they started to stretch out in a way the loss landscape that at first was so rough and so full of minima, making gradient descent to stop and to have so many difficulty. So this was stretched until a large flat region was formed in the middle and typically was explored by the training dynamics as it is in current application. So this is just a glimpse of machine learning and how this interaction between observation at the level of dynamics and landscape could tell us something on the landscape, which was this big mystery because it's a complicated system. Now, the plan is the one of moving to another subject, which is the problems in classical inference. And in this case, the plan is the one of applying this connection between landscape and dynamics on the other way. The idea is to, for inference problems that are simple enough, start by studying the landscape, and then from the study of the landscape, start to infer or predict what a gradient descent based algorithm could perform for such a problem. We started to implement this plan by focusing on a classical example of inference problem, which is called the tensor principal component analysis, and we will see some generalization of this original problem. Now, what is this problem about? You are given a tensor for which you know that it is the result of a rank 1 component, which is this part, and a noisy contribution that will affect independently the different elements of the tensor observed. Now, the task is the one of finding the rank 1 component, or in other words, the vector that would define this rank 1 component. Now, application of this problem for matrices are of course, nowadays classical. In finance, they go under the way of simple principal component analysis and in all lot of different branches, but also the application for tensor is on the rise, and you will see that this will turn out to be the more complicated and challenging case. Now, according to a classical inference strategy, the maximum likelihood estimator of this vector V is the vector X that would minimize the square error between the observed tensor and the rank 1 tensor that is obtained by this sample vector X. Now, when we do not care about the norm of the vector, so this vector is kept constant and we are just searching for the correct orientation so that it aligns on V, This minimization of this term here would correspond to the maximization of the product of the two tensor component-wise. So this is now reformulated in the problem. Here it comes the connection of this problem with glass physics, and you'll see it's a very direct connection, because a couple of line computations starting from the expression of the tensor, the original tensor itself, shows that this maximization problem corresponds to the problem of minimizing an Hamiltonian, or a risk function in this case, that has two components, a p-spin component where the couplings are proportional to the element of the noise, and a nonlinear field term that instead contains the information on the signal. This prefactor R here is called the signal-to-noise ratio, because it takes into account how big is the information on the signal with respect to the amplitude of the noise. So again, the aim becomes the one of minimizing such function. So very similar to p-spin, but with a little added field that will make a lot of difference. Again, for a vector of fixed norm, the search of a minimum for such an Hamiltonian takes place on the surface of an hypersphere in very large dimension that I reported here as this three-dimensional sphere, where we can say that the North Pole represents the signal, and the latitude of the vector x, which is the sample vector, we will call this latitude q bar, and is of course the projector of this vector on V, and this accounts on the fraction of the signal that will be retrieved by the sample vector x. Once more, we could think of using to minimize this cost function, a gradient descent based algorithm with some noise added or not. And this algorithm will start from a random configuration, which in this high dimensional sphere will typically be perpendicular to this vector we want to retrieve. So it will be located on the equator of this sphere. Now, the possibility of success or insuccess of this gradient descent dynamics, of course, will depend on the structure of the landscape that this dynamics will encounter along the way by starting from the equator. For a very big signal-to-noise ratio, we expect a convex situation in which the gradient will easily retrieve the signal. But then in the opposite case, for a very small signal-to-noise ratio, we might end up in a situation in which even the deepest minimum will not be correlated with the signal itself. Now, this is called a situation in which we are below the information theoretic threshold, which means that even by enumerating all the possible configuration, we would be not able to distinguish where the signal is pointing. Now, these are the two extremes, and of course there is the whole intermediate range of signal-to-noise ratio, which separates these two, and in which it is interesting to ask what a dynamics, how a dynamics will perform, how an algorithm will be able to retrieve the signal. And if this will be able to, if it will be able to retrieve the signal in a polynomial time or not. And then, of course, we expect that if the landscape visited along this search will be rough, well, maybe this will be enough to trap a gradient descent dynamics. So gradient descent might not turn out to be such a good idea for this problem. Let's see if that is really the case. As I said, we are going to focus on this tensor principal component analysis, but I want also to talk about a generalization of this tensor principal component analysis, which comes with this a problem in which the same signal is given under the form of a matrix and a tensor. So this will be a mixed matrix tensor principal component analysis. And instead of talking about one single signal-to-noise ratio, in this second example that we're going to look at in a few slides, we will be discussing the situation in which we have two signal-to-noise ratios as well. So this is all about the introduction of the model itself. And as I was saying at the beginning, the plan is the one of looking first at the risk landscape and then start to predict from it how the dynamics will perform. And then looking at the dynamics, we can also make the comparison on whether the predictions were correct. So starting from the landscape, to study the structure in very detail, what we did was to generalize a classical tool that is able to enumerate the stationary point of a random manifolds. And this tool is the famous Katz-Rice formula, which counts the stationary point by this delta function on the gradient at a chosen level of the risk function, and also at a chosen latitude, this Q bar here. Now, this formula has been used several times, but usually it is evaluated what is called the annealed computation. It is performed what is called the annealed computation. What does it mean? It means that this number is actually a random number, a random variable, which unfortunately fluctuates at the exponential scale. However, the typical value can be approximated or estimated by the upper bound that is provided by this annealed computation, which immediately evaluate the average of this quantity. It is lucky that in some of the problems this is indeed enough, because it can be proved that the typical case also corresponds to this estimation on the upper bound. But it was not, unfortunately, the case for our problem. So we had to actually perform the average of the logarithm with the introduction of replicas for realizing this. Of course, this was pretty challenging, but thanks to the hard work of Valentina, we were successful, and we were obtaining, as a result, the whole structure of minima in the landscape of this tensor principal component analysis, tensor principal component analysis problem. Now, one little remark at the end of this slide is that along the computation, we also needed to have information on the spectrum of the Hessian. And then this also gives, can distinguish, let us distinguish whether we are talking about stationary points, which are minima or saddles. And the result that I will report about our analysis is mostly the result about the minima that are present in the landscape. And here it is, the result. I'm plotting this, what we obtained in terms of the structure of the minima for the tensor principal component analysis in different cases in which we have this field that pertains the second part of this reformulation of the problem as this Hamiltonian with the p-spin and the field. When the field is linear, when the field is quadratic, when the field is cubic. Now, the second case, quadratic, corresponds to the matrix, so to the principal component analysis, and when the field is cubic, it's the tensor PCA problem. What you see in the figure is this red band. The red band represents the range in the latitude that corresponds, that will have a thick layer of minima in a finite range of the cost function. Also, you see the black curve, which represents the latitude of the deepest minimum in the landscape. Again, if you remember, the information theoretic threshold is when this deepest minimum starts to be correlated with the signal. So here you can see where the information theoretic threshold is always located in a different problem. Also, another interesting information is the one that comes from the most frequent minima, or the minima at the highest level of the energy, which are represented by these triangles here and here and here. Now, what is the result that we obtained from all these observations is that, well, when the we are talking about a linear field, everything is reported as a function, of course, of the signal-to-noise ratio. I shouldn't have forgotten that. So when the signal-to-noise ratio increases for a linear field, this is enough to let the whole band of minima moving towards a higher correlation with the signal. Situation is different for the quadratic field, where instead you have that this band actually starts to deform and split into different bands, but it stays on the equator, where it is this famous region where the dynamics start from, for a longer time, until minima destroys at the equator as well, at very large values of signal-to-noise ratio. And then here you find the hardest situation, where instead of the tensor PCA, where instead for every finite value of the signal-to-noise ratio, this thick layer of minima will be always there and will typically hamper any gradient descent dynamics that would, starting from there, attempt to find any information on the signal. And this is, I just anticipated that already, but we can use this structure of the landscape to predict the dynamics. And well, the prediction is pretty disappointing, because any kind of dynamics that will start to explore the equator and start to try to escape this thick layer of minima will have a very hard time to recover. Of course, one could think of a warm start from an intermediate region, and that for a reasonably high value of the signal-to-noise ratio can turn out to be successful. But if you start from zero knowledge, there is no way one can obtain a result with gradient descent. So that is the first conclusion that comes from the landscape. And then we moved to the observation of the dynamics. And we wanted to put the two things together. So in this case, I am moving to this slight modification of this problem that takes this form of the mixed matrix tensor principal component analysis. As I said, in this case, the channels the information comes through two channels. So we have two signal-to-noise ratio represented here by the two axes of this phase diagram. And the information that was represented in much more detail before now is compressed in one single phase diagram. We can recognize the presence of this region in which it is impossible to retrieve the information. And then we find this yellow region in which there is the information about a couple of different algorithms that attempt to perform the minimization. We have on one hand approximate message passing, which is not able to retrieve the information in a polynomial time in this small yellow region below the one line here. And then there is a much bigger hard region in this phase diagram, which is the one that corresponds to the region where Langevin dynamics or gradient descent-based dynamics is not successful in retrieving the signal in a polynomial time. So and then there is the final region, which is the green, where both these dynamics are successful. So what does it say, this result on the dynamics that was possible to obtain because this problem is simple enough? It says, first of all, that Langevin was was less successful than approximate message passing. And one natural question that came to our mind is why that was the case. Why approximate message passing was performing much better in this region here, while Langevin was being so much stuck and trying to make a better intuition on what was going on. What we did was to focus straight away on a point here and look at the dynamics of the retrieval of the information performed by approximate message passing in this blue curve here. You see there is just one little dot here before it gets a very high information on the signal. And here on the black line on the equator, in correspondence of the equator, there is instead the result that comes from Langevin. So it's really complete different performances, as it is represented by the fact that Langevin is having a very hard time. Now, again, we're trying to understand why that would be the case, why Langevin was performing so badly. And we came back to the information that we extracted from the landscape, in which if you remember, the case of a quadratic field corresponding to the matrix was not so bad after all, but the big troubles came from the tensor problem. So we decided that maybe it was a good idea to give up, at least at first, at the beginning of the dynamics, to give up the information that comes from the tensor, just to also get rid of the added noise that is also contained in this part of the problem. So we thought of performing a gradient descent dynamics that would only consider the matrix component at first, and then use the whole information that is progressively reintroduced in the problem along the way. Again, we just keep aside a component of the information, but we still perform a gradient descent dynamics. And the result that we obtained with this procedure is the following. So this is the gradient descent that is obtained by retaining the information on the matrix at first and then putting back the information on the tensor to reach at different speeds, and here it comes the difference from the on the curves, to reach the actual whole information that one can retrieve at a long time, at longer time. So there are two comments at this point. The first is that this was successful in the sense that by this little trick that was based on the knowledge of the landscape, we were able to shrink down the Langevin hard phase up until it was just corresponding to the approximate message passing hard phase. So we were closing the gap between the two algorithms by putting this extra information that came from the landscape. And the second comment is that unfortunately, this is not a general case. Of course, this comes from the very specific structure of this problem, and we could exploit this structure to obtain this result, but it's not yet general enough so that it can be applied in general to improve gradient descent dynamics. Now, rapidly, I want to give another, I want still to use this mixed matrix tensor PCA to say something more about this connection between landscape and dynamics, which turned out to be very, very interesting. So I report again, I forget about approximate message passing and also the information theoretic the region in which it is informationally theoretic impossible to retrieve the signal, and I just have the hard phase for Langevin dynamics compared to the easy phase. Interestingly, by performing the exact cuts, sorry, I forgot to say, in this case, we are coming back to this problem in which, so the result of the dynamics again are the one in which we consider both the channel always present at the same time since the beginning of the dynamics. Now, interestingly, in this work, it was observed that the landscape, so it was studied the landscape, and it was observed that the structure of the landscape at the equator was becoming simple, meaning that all the minima were disappearing only at this level here, on this purple curve. This is a curve that is called the trivialization transition, where the landscape becomes simple. And this poses a big trouble because it's kind of paradoxical, because there is this region here in between these two curves in which it seems that the dynamics is, gradient descent dynamics is plainly successful, but the information that comes from the landscape is some way telling us that it should not be the case, because the landscape, especially at the equator, is full of minima, and the dynamics should not be able to go through them. In particular, they are expected to be exponentially numbered. There should be no way it can go through this region. So to understand and solve this paradox, what we had to do is to give a very close look at the features of aging dynamics and at the details of the landscape structure. If you remember, I was describing this aging dynamics since the beginning as this exploration of saddles at progressively lower level of the energy until this first layer of minima was reached. And these minima are the most numerous, are the highest in energy, and are the flattest among all the minima, which means that in some sense they are the most fragile to perturbations. And this was the case for the p-spin, but in this case, in the case of this matrix, mixed matrix tensor PCA, we have a perturbation which is represented by the field that contains the information on the signal. And it is this perturbation that makes this minima, breaks the stability of this minima. So they are the first to become unstable when this perturbation is applied. Now, the mechanism with which this occurs is goes under the name of BBP transition because it is it's something that was studied in randometric theory, and it is the transition that is described in a situation in which you have a spectrum of the distribution of eigenvalues, which has a continuous part, and then at a certain point, changing one parameter of the problem, there is one single eigenvalue that pops out from the continuous part of the spectrum. And it is exactly this situation which is occurring in this problem, in which we have this semicircle law for the minima at this highest level of the energy, which is touching zero. Okay, so when this BBP transition occurs, this isolated eigenvalue pops out from the left, and it becomes immediately negative, which means that this minima becomes unstable, and in fact they are showing the way to the dynamics towards the signal itself, because it can be shown that actually the eigenvector that corresponds to this eigenvalue has a finite correlation with the signal itself. And it is very surprising after all, because it says that this dynamics, thanks to the first layer of trapping minima, will be actually able to escape to the whole structure of other minima that are still formed and present underneath. In some way, this dynamics is flying over these other minima, and by this mechanism, able to escape this rough region and able to retrieve the information on the signal. So this, again, turns out to be a very interesting mechanism that was not at all expected at first and only came out because of the very deep understanding of this connection between landscape and dynamics that was developed starting from the study of the p-spin problem. Finally, I want to give, still on tensor principal component analysis, I want to give a glimpse of this other work in which, again, we use this intuition that comes from the information from the knowledge of the landscape to develop, in this case, a general strategy, which was missing a couple of slides before, a general strategy to make gradient descent competitive. Now, and in fact, actually to achieve the performances of what are thought to be optimal algorithm. We are back for this work to the pure form of tensor principal component analysis, and in particular to the case in which the exponent is here k is equal or larger than 3, which is the hardest problem. Now, for this problem, I said already the information theoretic threshold is of order 1, and it is approximate message passing actually performs analogously to gradient descent, and they don't have a finite signal-to-noise ratio at which they achieve the information on the signal on a polynomial time. So actually the algorithmic transition for those algorithms is infinite for the infinite system size, but for finite system size, it scales with the system size with a certain power law. There are some very optimized algorithms that work with by just contracting the indices of the tensor. These are called tensor unfolding and sum of squares that are proved to actually work better than the previous class and have an algorithmic transition that still is scaling with the size of the system, but with a smaller power. Now, what we wanted is actually understand why gradient descent could not perform better. And in fact, our challenge was, can we actually match the performances of tensor unfolding and sum of squares? And now, to try to improve gradient descent, we thought back again to this, what is the actual problem the gradient descent meets? And of course, the problem is, as you now have heard many times, is that it is bothered by, of course, this rough landscape, which is always there, and in particular for the tensor is very important, especially on the equator. So what we did to diminish the problem that this landscape poses is proposing a dynamics that actually samples the landscape in many points at each single step, and then uses this average information on the gradient evaluated at all the different points for performing one gradient descent step. So the idea is that on average, the operation on this average operation on the gradient in different points will be able to suppress the random contribution which is originated by the noise by, on the other hand, keeping unaltered the contribution that comes from the signal. So more in details, the algorithm goes as follows. We choose R random points on the sphere, and then we evaluate their center of mass. Then we evaluate the average of the gradient of the cost function on these R points, and we use this average to evaluate the new position of the center of mass at the second step. And then we perform a further sampling of the landscape, which is, again, just conditioned on the fact that the new center of mass must be the one just evaluated at the previous step. So this is the procedure in detail. And this is a bit of the picture of how this procedure would perform, would be realized on the sphere. It's interesting to think of the fact that at the beginning, all these random sampled vectors are on the equator, so the center of mass will be typically standing on the center of the sphere, and then this will be the movement of the center of the sphere and a new sampling and a new update of this center of mass for this cloud of sampling points. And I want to show how this idea, what result this idea gave. We call this algorithm the averaged gradient descent. How does it perform for k equal to 3 when the algorithmic transition of normal gradient descent goes as n to the power of 1/2, while the most optimized algorithm go rather with n to the power 1/4. And here you see the result of that numerical result, in which you find the information on the signal retrieved at the end of dynamics that are performed in this way for different values of the size of the system, and also for different values of the signal to noise ratio, which has been rescaled so to obtain a crossing of the curves. And this is telling us that this rescaling is actually giving the actual growing of the signal to noise ratio as a function of the size of the system. So we have a first indirect evidence that the average gradient descent is actually performing as good as the most optimized algorithm that were developed for this specific problem. Now, I say the first evidence because we wanted actually to be better sure of that was the case. So we went closer, gave a closer look at the behavior of this algorithm, and we were seeing that it is interestingly. So these are a representation of dynamics in terms of the actual size of the vector that represents the center of mass and the amount of signal reconstructed along the dynamics. So this average gradient descent dynamics, interestingly, is separated into two regimes, and the first one is collecting little by little when the center of mass is not yet on the sphere. You see that there is a adding of information on the signal, and when it lands on the sphere, there are two completely different behavior emerging in this second regime. So what we did once more was to ask why that was the case, why these two different behavior, and the answer came from the landscape. The idea is when the center of mass lands on the sphere, depending on whether it finds a rough landscape or a convex landscape, it will be able to retrieve the signal or not. So by using this information again, we were able to theoretically find this information on the scaling, expected scaling of the signal to noise ratio for the actual retrieval of for the algorithmic transition of averaged gradient descent. And well, I'm definitely running out of time. I want just to make a point that is the point on this average gradient descent, which is the fact that at variance with the previous trick for the gradient descent to perform as well as approximate message passing in the mixed matrix tensor PCA, this average gradient descent has the potentiality of being very general because it inherits all the features of, or the potentiality of being generalized as gradient descent by just adding this trick of the average that can always be performed. Now, talking about generality, I had this final example on how general can be also this other interesting mechanism that I was explaining to you about this instability of the minima that are at the highest level of the landscape. And this was given in terms of another inference problem called the phase retrieval, in which the situation is completely different, but the vector that must be recovered in high dimensional space is obtained by the information on the vector we have is its projection on a collection of random vectors, x of m. And in this case, we have all the algorithmic transition for approximate message passing and the gradient descent as well. And the prediction is that, well, gradient descent will be able to perform nicely when the minima will disappear. But we saw evidence once more of this mechanism for which, even if minima are there, it seems gradient descent is able to retrieve this information, giving again a first other evidence of that this mechanism might indeed be general beyond this tensor principal component analysis, including this problem of phase retrieval, and it makes us hope that that can be even more general as a whole. I mean, I want to stop just showing you the list of the results that I wanted to present in this talk. I made a list of questions which are mostly concentrating on this idea of how general are the mechanisms that I have showed so far, especially this BVP transition for the retrieval of the signal, and also how general this average gradient descent can be seen to perform nicely and probably to match the to match the results of the best known algorithms in the different problem. And this answer to these two questions, which we want very much to explore better, is leading us to a bigger question, which is whether all the information that can be obtained from such inference problems is actually contained in the landscape, and whether by using this landscape or developing algorithms that optimally use this information in the landscape will tell us what are the actual best algorithm for the different problem. And then, of course, there is this final result that might be even more exciting on extend that beyond the scope of this inference problem and go back to the problem of machine learning, where the whole landscape itself is even more complicated. So whether we could then apply what we have understood on how to optimize the dynamics from on inference on the other case as well, on the machine learning setting, to obtain even better result in that field as well. So, well, with that I conclude. I'm sorry I took a little bit longer than expected, and I thank you very much for your attention.
Thank you, Chiara.
Okay, so thank you, Chiara, for the very interesting talk. I think we have some time for questions, if there are any. So I see that Sergio Caracciolo has a question.
Yes, I saw that in the definition of your average gradient descent algorithm appears a parameter R. Is this parameter kept fixed or is scaled with the number of degrees of freedom n?
Okay, the parameter R, we checked for different values of R, and it does, okay, so to obtain optimal performances for average gradient descent, there is a maximum R that is that must be used. And if I remember well, this maximum R is scaling, yes, with the number of the parameters. It's a non-trivial power of n itself. Okay, does this answer?
But the best performance is obtained with what values of R? When you, in your plots, you are giving results varying the number n. Okay.
Yes.
Then
yes. Do I remember?
Is R kept fixed or is it scaled with n?
I don't remember this particular result, but because probably in this case, so for the specific structure of this problem, we could actually perform averages by using infinite R. Okay. Because we could, I mean, that's a lot related with this idea of this index contraction. So for the specific structure of this problem, we could we could obtain information on the actual expected value of the gradient. So this result, if I remember well, were obtained from the expected value of the gradient, rather than this empirical sampling as I was presenting here to give you more of an intuition. Because this expected value is only able to be, I mean, we can only obtain that for the specific case of tensor principal component analysis, again, for the specific structure of the problem. But then we compared this, so this is obtained for the best, I mean, this expected value of the gradient. And then we compared the result that comes also from finite value of the sampling, so the point at which we sampled the landscape, and that was showing that you reach quite fast the performances of the best possible algorithms by just increasing R to, I don't know, like 5 or 10, something like that.
Okay, thank you.
Okay.
Okay, any other questions? Okay, I see that Roberto Livi has a question.
Chiara, just to understand your message. So you are just showing to us that essentially, when facing with these kind of problems, the main message, as far as I understand from your seminar, is that this average gradient dynamics is presently performing very well, much better than any other available algorithm, or not? Is that the message?
Well, it's not better because, I mean, we have seen that we have seen how that this average gradient descent perform. We've seen it only for Tensor PCA, and in that case, we found that it matches the performances of the best algorithm. So one of the possibility is that, I mean, the big problem is that these best algorithms for Tensor PCA are very ad hoc, again, based on the structure of the problem and so on. So for a different problem, one should need to develop a whole new algorithm that would, again, match that structure and so on and so forth. So the advantage of this average gradient descent is that it will match the best algorithm, but then how to apply it to a different problem, it seems it's much more easy to figure out. So that's a bit of the idea. The hope is the one of finding an algorithm that can be used in different contexts, and then it can give you very good performances and actually best performances. And also, there is this connection with the landscape that it is possible to have in the gradient descent dynamics is also giving you a lot of intuition on why you cannot do better than that. So this is the big question I was mentioning at the end. So if it doesn't exist another algorithm that does better, maybe we have, reached the bottom of the problem and said, okay, now we have an algorithm that we can make it to perform at best. It is exploiting at best the information which is contained in the landscape, and we know why it cannot do more than that. While for the ad hoc, you say, okay, this is the best for the moment, but there is no understanding on why that is the case. So there are some discussion. There is a discussion like that in our paper, because there is a very interesting problem for this Tensor PCA. These algorithms ad hoc developed for Tensor PCA perform differently for k even or k odd. Oh. And there is no way to understand why. So for k, in one of the cases, they make a conjecture on how that would work. On the other case, they can prove, but there is it's not easy to understand why they cannot make the proof for all the cases and why the mechanism is so different. If you look at the average gradient descent, you understand what the problem is. It's very explicit. And it is related with the fact that for k even, the problem is symmetric. So you have a problem with the gradient, because when you try to average out, the gradient can point in the two directions. Mm-hmm. So you cannot use the gradient anymore, and that is what we use, we use the Hessian. So we have a different structure from k odd and k even, and it is fully explicit and is related to the structure of the problem, to the structure of the landscape, and so on. So we have a better understanding of the problem and of the limits of the problem. And that is, I think, the advantage of that particular algorithm I was presenting.
Yeah, but let me be a bit slightly philosophical. I think that all the people which are involved in this kind of job essentially would expect in their mind that probably you can develop general strategies to approach this problem, because if the fate would be that for every problem you have to cook your algorithm, I mean, that would be a bit disappointing.
Precisely. So that's what we try to avoid by thinking of this averaged gradient descent. That, you know, the reason for which it is used, the gradient descent, is that this is the first thing that one can think of when wants to minimize something. And it is very versatile. It goes exactly in the direction of avoiding to cook things on purpose for specific problem, which is something that is a lot done actually nowadays.
Yeah. Okay, thank you very much for your answer.
Okay, any other questions? Okay, so if there are no more questions, I think we can thank again Chiara for the very interesting talk. Thank you.
Thank you all.
Thank you, Chiara. Interesting.
Thank you.
So goodbye, everybody.
And bye-bye.
Bye, everybody.
Bye, thank you, bye.
Bye, thank you.
Ciao. A tutti.
Ciao.
Ciao.